All right, welcome in everyone. My name is Abhirup Vijay Gunakar, and welcome to today's presentation. The title of today's presentation is Understanding Data Races in the Linux Kernel System. A little bit about me. I'm a student and systems security researcher at Arizona State University back in the US. I just graduated with my bachelor's in computer science this past May, and I'm continuing my master's. I'm also the chapter lead for Google Developers Community at Arizona State University. So we also try to follow a lot of open source tool and keep ourselves up to date. All right, let's begin. Context and stakes. So, quick pulse check. Which of these have you personally hit or worried about? We can do a show of hands. The consequences that we basically face with data races: system crashes, or silent data corruption, security vulnerabilities, or all of the above. Anyone here? Quick show of hands. A, B, C, D. A, B, C, D. All right, everyone is in the correct room. It's all of them are correct. So, in short, data races are, they're scary. Other than, all of these things, there's a lot of stuff that is going on with data races that occurs and we're not even aware of. Concurrency bugs are notoriously hard to reproduce and diagnose, and non-determinism and rare interleavings are a big reason. Now, let's align on what a kernel data race actually is, and then we'll take a look why they are so costly and why we basically need to fight them. So what are data races? A data race basically happens when two or more threads or CPUs try to access the same shared memory region without proper synchronization, and at least one of them has like a write access. So as we can see, the results can be unpredictable. Inside the kernel, this is extra risky because it can corrupt internal structures, cause Heisenbugs, which we get to know about many late stages later, and we're not even aware when they're happening. And they basically also open up a lot of security vulnerabilities. The hard part about data races is that they depend on timing and interleavings. You might run a test 1,000 times and never hit the batch schedule. If we take a look on the diagram on the right side, we can see that both of the threads have read and write, and they don't have a specific order. Neither of them, they are using semaphores or atomicity or anything, which shows that it's pretty bad. Both of them can try to write at the same time, which can basically cause a data race. Now, we know that it is bad, but how bad it is, like in reality, how bad it can be. So how costly a data race can be, let's try to understand it in terms of industry standards. Let's zoom out to cost, and even outside kernels, concurrency bugs and their cousins, like data breaches from settle bugs, they're expensive as well. According to this survey by IBM, which they do every single year, there's a cross potential of 10% increment every single year. For 2025, it's an expectation of over $5 million US. This is just because of data breach. And kernel races aren't the only cause beside these data breaches, but they're part of the necessary issue, and they're rare, and basically they cause catastrophic failures. Now, here's the plan for the rest of the talk. The roadmap. Why kernel data races matter, concurrency mechanisms and pitfalls, and the tools we'll use: TSan, ThreadSanitizer, and KCSAN, the kernel sanitizer. ThreadSanitizer is used in user space, and KCSAN is used for kernel space, and the best practices that we can use in order to avoid these data races. First, let's see why kernel data races matter. All right, they cause unpredictable behavior, classic Heisenbugs that disappear when you add logging or a big breakpoint. The worst is silent data corruption. Everything looks fine until it isn't. They can become security issues when attackers exploit inconsistent states. And they're hard to reproduce, so we need tooling. And they're not just clever reasoning. We need to use the essential tools to fight these data races. If we take a look at the right side, it's basically a pun, but it's quite accurate. Observing can change the timing and hide the bugs. Like in Heisenbugs, it's like, just don't look at the screen and it will go away. But in fact, it is there. But if we don't look at the screen, and if we look at the screen later, we just won't realize that there was a bug. Now, related to that, here's why these bugs escape during testing. As we can see in this diagram, the error can occur here, like somewhere at the start of the process. But we will only realize it or only be able to notice it until a billion cycles later. And between these things, a lot of logs are logged. And there's threads, a lot of rescheduling, caches flush. And that's why this effect is brutal. Now, this is why we need runtime detectors and reduction techniques. Now, let's ground it in how Linux creates concurrency in the first place. Concurrency in Linux. Linux is symmetric multiprocessing, which means multiple CPUs, cores execute kernel paths in parallel. There's preemption and interrupts. Code you thought was atomic can be paused, and so something else runs, which is quite advantageous in some ways. There's a shared kernel everywhere, reference counts, lists, device queues, and races often show up at boundaries. Let me show you a quick picture, which basically I use as a mental model. So if we take a look at this diagram, we see multiple cores of the CPU, the 4 cores essentially, executing concurrently. All roads lead to a shared kernel state here in the middle. And it's basically a run queue, device is struck, inode cache, whatever. Those bidirectional arrows are reads and writes from different contexts. Without proper locking or memory ordering, interleavings can violate invariance. Even if each CPU's code looks correct in isolation, global correctness depends on the order of operations in these CPUs. So if we take a look deeply, this shared kernel state is shared between all these CPU cores, which causes concurrency. Now, how we can avoid these concurrency bugs, there's a lot of different ways, but atomics and memory barriers is one of them, which we'll come on to later. Now that we are aligned, let's try to take a look at different techniques that we use and the tools that we can use, like the ThreadSanitizer and the KCSAN. Before I'm gonna show you like a quick example of how a data race occurs before I actually come on the TSan and the KCSAN topic. Here's a tiny race example which I wrote in C. So we can see that here's the smallest, it's a very small possible data race. We have a shared global counter, and there's an increment counter which does a read modifier, write race. It reads counter, adds 1, and then writes back. Reader reads the counter and at about the same time. If these two interleave just wrong, reader may see a stale value or 2 increments collapse into 1. That's the core hazard. At least one axis is a write, and the axes are not synchronized. This exact read modify write pattern shows up everywhere in kernels: fast paths, stats counter, and driver flags. If we take a look at the diagram, left lane is thread 1, and the right one is thread 2. It increments, it writes, and they basically do the same. Now, if both read before either writes, you lose an increment. If one reads while the other writes, reader can see in between state, which basically causes the data race. So, how do we prevent these data races? There's certain core techniques that we can use, it's not 100% guaranteed or sure that we might be able to prevent a data race, because all data races cannot either be detected. If we cannot detect something, if we cannot see something with our own eyes, or if we cannot get to know about something with our own experience, how can we even prevent it? There are certain things, best practices and techniques that we can use, and tools, which I'm going to talk about. And other than that, it's basically experience. The more we experience it, the more we realize that there's a data race that's happening. All right, synchronization mechanisms in the Linux kernel. So from here on, it's quite practical. First, we'll talk about synchronization primitives, and then ordering, barriers, and then why we still need these dynamic tools. Spinlocks. So busy wait mutual exclusion. Great when you can't sleep. It's basically a interrupt or preempt disabled context, and critical sections are short. We don't need larger critical sections for them. Mutexes, sleep if the lock is contested, and used in process context where blocking is okay. Read-writer locks, basically many readers, one writer, handy for read-heavy shared data where we have to read a large amount of data, but we only have to write once, or not multiple times, or not as many number of times as we have to read. And then we have the RCU, which is read, copy, update. Readers are wait-free. Writers publish a new copy and retire the old one after a grace period. Perfect when reads dominate. Now, atomics and memory ordering. Locks prevent simultaneous accesses, but modern CPUs also reorder memory. So we also need ordering guarantees. In this slide, we can see we're talking about these two specific topics, out of which I find atomic to be quite interesting. The only reason is because atomic operations are the only operation which makes updates indivisible. There is no turn, read, modify, write. We can, basically do them all together, but it's not tearing up the function or the operation at one point. In Linux, we pair atomics with ordering, like SMP store release, SMP load acquire. SMP store release basically makes earlier writes visible before this store release, and the latter basically ensures later loads happen after this load. Without the memory ordering, CPU's compilers may legally reorder independent ops, threads, and then see events out of order. The last one, compare and swap. It's basically a fundamental atomic primitive, or you can call it as a workhouse primitive, for lock-free algorithms. It compares the old value, and if it matches, it swaps atomically. I have attached a link of all the documents at the end of the slide. I've also shared the slide, so you'll be able to access it if you want to. And beyond atomics and memory ordering, beyond acquire, release, sometimes we need a stronger fence, enter the explicit memory barriers. This, which I referenced earlier. So what are memory barriers? Linux gives us 3 core SMP barriers, symmetrical processes. So SMP MB, SMP RMB, and SMP WMB. What is MB? It's basically a full barrier. Orders both reads and write. RMB, basically, it's like a read barrier, and WMB, it's a write barrier. They stop reordering across CPUs and across compiler optimizations, crucial on weakly ordered architectures, and many kernel operations, like locks or scheduler calls, implicitly include barriers. So you often don't need to insert explicit ones. Now, if we take a look at this diagram where we have 2 separate cores, the CPU 0 and the CPU 1, this shows why. The cores caches and store buffers and invalidation paths basically mean that other CPUs won't necessarily see your writes immediately or in order. Barriers force the visibility in the write sequence. It's basically we are doing sequencing, but in the correct order. We're trying to make sure that our individual functions are being implemented correctly. Now, even with the right primitive and fences, static reasoning misses real interleavings. There can be some negative logs, and that's another reason why we use dynamic data race detectors. Again, the KCSAN and the TSan. Why we need to use dynamic data race detectors? I mentioned one reason, but that's not the just quite sufficient reason alone. We need a broader perspective to understand the dynamic data race detectors. Static code review, like static reasoning, can miss races as it's too complex and there can be hidden paths. Compilers and CPUs can legally reorder loads, stores, under weak memory models, and races can only appear at one time. Bugs often depend on rare timing, like Heisenbugs, the diagram we showed earlier. There could be times when we look at the bug and we will realize that there's a bug, but it's only a billion cycles later, or if it's like too late, and then we realize there's no bug, but it is actually over there, but we just can't detect it because there's a data race happening. Now, what we're going to talk about is, which we have been talking about quite a while already now, is the TSan and the KCSAN, and basically how we observe the actual execution. We'll also take a look at some of the KCSAN reports, how the reports look like, and how it works in real life. So what are these tools, and basically why should we even use them? TSan, as I gave a brief intro earlier, it's used in user space. I personally have used TSan quite a few times, and it's used especially if you are coding in C programs. It detects the data races at runtime, has compiler instrumentation, and inserts check around memory accesses and synchronization. It's very effective, but another reason it's quite heavy, quite resource intensive. Another part of my research has been to working on algorithms which are quite effective and are a bit more lighter than TSan, ThreadSanitizer, basically doing the same task, but we don't need quite intensive hardware or the resources in general. Now, KCSAN is basically a kernel sanitizer. It uses watch points, plus it's using sampling to catch data races and unsynchronized read-write pairs, which must have low overhead, and it's basically designed for large systems. Now here's a quick comparison table for the TSan and KCSAN. TSan is used for apps and libraries in C++. KCSAN used in Linux. Approach: TSan uses compiler instrumentation and KCSAN uses the hardware. Coverage: TSan checks every access. KCSAN is probabilistic. It does miss out some races. And use case: for TSan, we can use it for user space multi-threading issues, or where we have a resource-intensive program. But kernel data races can be detected using the KCSAN as it works across subsystems and drivers. Now let me show you how KCSAN looks like in action. So KCSAN is built into the kernel tooling. We can enable it using config underscore KCSAN is equal to y in the kernel config. We can basically call it. And it places watch point and samples memory accesses. When it sees conflicting operations without proper synchronization, it will print a report for us. If not, it won't. So as we can see, it's quite easier and quite useful to use KCSAN in a way. Now, reports include the two racing accesses, read versus write, the addresses and the sizes, and stack traces for both sides, sometimes with the observed value change. As we can take a look on the diagram on the right, we can see that there's a CPU core, CPU 0, let's say, and it's racing with a read on CPU 6. Note the call stacks and the value change line. It's super helpful for triage. I have attached the source, docs.kernel.org, and the link is at the end of the presentation. You can take a look at that. It's quite useful. Now, all right, so one other question which occurred to me while I was making this presentation, which is quite important, is how do you read one quickly under pressure? Like reading a KCSAN report. So reports basically look like, they start with bug. KCSAN, it looks like a normal kernel varying. It lists the conflicting accesses, like read versus write, their sizes, addresses, and which tasks CPUs triggered them. This tells you what raised. You also get stack traces for each path. This tells you where to add locking or barriers. Sometimes you'll see an observed value change, example 0x0, 0x1, if detected, which helps confirm real corruption, real data race, real data corruption. Now, first triage question, let me ask you everyone over here. Are we missing a lock, or do we need to acquire or release an explicit barrier between producers and consumers? Now, coming to the concept of this whole report that we were talking, like how we can read a report. With detection and triage covered, we'll wrap with a simple prevention checklist and basically best practices. Here's a sample test report which I ran, and then this was the result that came out. So this is what happens when we try to run a KCSAN report. This is a real report. It basically triggers a kernel warning, like bug, KCSAN data race is your red flag, something like that, or whatever it's detecting. It names the conflicting functions, names the conflicting paths, it names the conflicting barriers that we're using, and it's basically tells you that, test kernel write, test kernel read, what's wrong in those processes, and shows the address size that basically raised, tells you the exact physical address, the virtual address, when we are trying to trace it. Now, each side gives you a stack trace, and with the task ID, the CPU, and it's super helpful to understand while we are scheduling here. Like, for example, task 1, 2, 3 on CPU 0 wrote, task 1 to 4 on CPU 1 read, when one of them had a write access and got the better of it. Now, another way to read it quickly is basically scan top to bottom, basically see who wrote what, like what was the report written by KCSAN, where and when, and then who also reads and who writes. Note the offsets are the symbols, like 0x20, 0x50. These basically pinpoint the exact instruction within the function, and if present, the value changed tells you the before and after, which proves the race had a visible effect. Okay, so KCSAN is handy. In short, in the past 2 slides, we got to know about KCSAN is a data race detector, how we can use it, how we can read the report, how effectively it prevents or basically catches data race. But it isn't magic. Everything has its own pros and cons, as we all know. So let's be honest about the limits, the limitations of KCSAN. It's quite probabilistic. And as we know, probability is like you either get the shot or you lose the shot. But a quite good thing about probability is it tells you in time, no matter what are the odds, like how many odds are there that you're going to get a data race or not. So KCSAN is quite probabilistic, but it can also have false negatives like any other tool. It focuses on data race, not full memory modeling reasoning. It's quite subtle in ordering bugs that need strict LKMM analysis, and they might slip by. False positives are rare, but again, they're also they are possible. For intentional RACI reads, we have to use data race expr function and data race RACI to suppress intentional RACI code paths. It's not for production. The overhead is fine, but we have to, make sure that we don't have to ship it. Like it is not for shipping kernels. It's not for production. It's just for test development. We can use it as a internal practice when we are making the programs. So how do we actually prevent these races? Let's shift from detection to prevention. We can take a look over here. I have a diagram on the right side. I'll refer to it in a second. But before that, what we can do is we can use correct synchronization primitives, semaphores, use memory barriers, like what we talked about before. Spinlock T over here, it's a short atomic critical section, basically an interrupt or a preempt, which we can use. Struct mutex when sleeping is acceptable, processes context, but it's for longer sections. RCU, it's for when it's read heavy or it's mainly dominated by read. And readers are wait-free, writers update via copy and swap. And it also has a grace period. We already talked about copy and swap before, but just mentioning it over here. All right, now let's take a look at the diagrams on the right. We have 3 specific diagrams, diagram A, B, and C. In all of these diagrams, circles are states, and each column is a thread. We can take a look at it. And they have the lock and the unlock nodes, which basically shows the acquisition order. The key idea is every thread takes locks in a same global order. Example, A, B, C, and all of them. Then releases it in reverse. Now, releasing it in reverse, it basically follows a consistent order, which avoids classic deadlocks and eliminates many ad hoc fixes later, which saves us quite some time. Now, beyond locks, 2 themes save you repeatedly. Basically, reduce sharing, like the shared memory zone, and reduce memory ordering. These are other 2 best practices which we can use to prevent data races. One of the other things is minimize shared state, prefer per CPU or thread local where possible. If we have extra CPU cores, assign specific tasks to only certain CPU cores rather than assigning a single CPU core to many read-heavy or write-heavy tasks. Memory order discipline. We can basically wrap across CPU reads like read once and write once. We can memory order in ways that the tasks which are only reading, they should go and read first, allow sequences, writes should be written in the similar order. And we can also use atomics, like this function over here, and barriers, like the SMP store release, SMP load acquire when consuming it. Leverage tooling, we can run log deep, sparse, KCSAN regularly in our command line to catch issues early. Now let's distill that into a short checklist so that we all are prepared when we are running our programs, how we can avoid these data races. One of the things is use the right synchronization primitive. We talked about 4 of them in the previous slide. We have to make sure that we are using the right primitive. Follow lock ordering consistently. Avoid A to B or B to A, elsewhere. It should be in one place. It should be consistent. And wrap shared data accesses with read once, write once when needed. Apply atomics plus barriers. We've been talking about it for quite some time, but it's a really good practice, and it's quite efficient, comes quite handy when we are actually trying to cache data races. Minimize shared state, which we talked about. Prefer per CPU or thread local. Run with KCSAN enabled in debug kernels to cache data races early. use log deep, sparse, annotate intentional races with data race, and review code for rare interleavings and stress testing. All right, this is the last slide. After that, I'll open the floor for questions. Key takeaways. Data races are real. They're not something imaginary. They can cause corruption, they can cause crashes, and they can basically create security bugs for us. Reasoning alone isn't enough. Compiler reordering hardware, or compilers reorder, hardware is weekly ordered, we need tools. Not everything is perfect. We need dynamic tools like the TSan and the KCSAN to help us detect these data races. KCSAN isn't perfect, but again, it's probabilistic and not for production, but it's great in development, great in testing. Prevention is key. Use the right locks, semaphores, synchronization. Primitives, read, write once, atomics, barriers, and a defensive workflow with lock deep or sanitizers. If I would be sitting on that side of the seat, like if I would be part of the audience, since it's the last slide, what I would take away from this, whole talk is that make data race detection a safety habit, not like something that we will check out casually. It's a best practice. For example, if we are using command line, those of us over here who write a lot of code in Linux, we use a lot of tools. We know that how handy it is if you're just using keyboard shortcuts. It's basically, we memorize them instead of typing the whole words or like using the whole functions. If we just use the shortcuts, it's a habit. So that's what I would try to take away from this talk. All right, let me open the questions first. Any questions? Yes.
Is KCSAN able to detect deadlocks?
Yeah, it can. Yes, KCSAN can detect deadlocks. Yes.
From your personal experience, did you get any false negatives? So
yes.
KCSAN missing? And how often did you get those? Is it 1% of the time, 50% of the time?
It happens quite a lot. It's like, let's say I'm writing a program which has a lot of read cases, then the probability in that case is different. Sometimes there could be Heisenbergs, and then, and sometimes their Heisenbergs are not there. So it's like the probability is completely different. It's like odds vary. But what I'm trying to work on as a researcher is trying to work on these efficient algorithms where we can try to lower the overhead, and which is also not quite hardware or resource intensive, but we can try to avoid these data races. However, KCSAN's approach is quite effective in that way. And answering your question, which you asked, how many number of times, it's quite uncertain. It's like, there's this one tool. Let's say, let me give you a very practical, real life example. Let's say we live in a building where there's a chance, God forbid, that a fire might happen. What we can do is, basically, keep these fire extinguishers, like at least 10 fire extinguishers in a room which is full of 10 or certain amount of people. It's basically a game of probability in that case, like who knows how to use it correctly at that point. It's like we cannot completely make sure that everything will be followed in correct order, but it's just the safety precautions that we are taking. Yes.
And do you have experience? Sorry.
No. All good.
Do you have experiences running KCSAN on the preempt-RT kernel? And
Sorry?
is it, there's the real-time kernel like Linux preempt-RT.
Right.
Do you have experiences running the ThreadSanitizer on this kernel version as well? And if so, is it also done in kernel CI? Do you know that?
Yeah, it's done in kernel CI. I've used in kernel CI, but not in that specific version that you asked.
But this would be quite interesting because there the locking mechanisms are changed. Mm-hmm. So it would be good to see if things still behave as they should.
It will be, yeah. That's quite interesting, yeah. It would be something actually I will try to take a look at. It's quite interesting. Thank you. Yeah.
What is the overhead of KCSAN, and could you alter the sample rate?
Yes, you can alter the sample rate. That is possible.
Yeah, and is it what is the overhead
In terms of, are you asking in terms of number or like?
performance? Or
I would say it does function 75% of the time. If I will, again, for KCSAN, I try to talk in terms of probability in that case.
yeah.
But it does function 75% of the times in the programs that I have used it for.
Yeah, because if it delays, it might hide some bugs.
Yeah, because there are certain bugs which do exist and you only get to know after certain cycles later. But it's like if you completely integrate KCSAN, TSan is much more effective, but it's for user space. KCSAN, when we use it for kernel, the good thing about KCSAN is it's, you know, at least 2.8 or 3 out of 4 times you will be able to know that, okay, there's a database that is happening. Yeah. Any other question? Yes.
What about use after free?
Sorry?
What about use after free? A
Uh,
little bit off topic, but
use after free pardon. So try to listen to
there is another class of arrays where you can release your memory free,
Mhm.
and you can try use it after that. That's use after free.
Like reuse the
The free memory, yeah.
Oh, the free the memory? You mean?
When you free your memory and you don't know your pointer, and you might try again use it, but it's not valid anymore.
Right, yeah, because you.
Would KCSAN help catch such situations?
Let me try to frame your question if I understood correctly and let me know. So you mean when we have freed the memory, right? When the pointer is not pointing to the correct part of the memory, and then your question was?
And then you access it.
Then we try to access it.
Yeah, that's you use after free, which can lead to undefined behavior.
Yeah, it can. Yeah, because you have already freed the memory. It's not pointing to the previous part of the memory. That's.
Maybe a comment regarding that. I mean, this is not the ThreadSanitizer, but address sanitizer topic, and this tool should be able to catch it. Because it's like the user space address sanitizer just for the kernel.
Yeah.
Yes, but this happens if the structure is corrupted. So generally, this case could happen if you have a data race, you have corrupted your data. At the end, you are accessing an invalid address.
Yeah, but usually then in the ThreadSanitizer you catch the data race and not the address. They use after free or whatever reference counting when it goes off there, and then you see the problem and then you fix that, and then you can have a look with address sanitizer. But I think you cannot run both tools in parallel, right?
Yeah, they cannot be run in parallel. For the ThreadSanitizer, we are basically trying to catch the data race. That's correct. However, that might be quite an interesting question for a research topic in general, when you're saying that when the memory has been freed, the pointer is not pointing anywhere, because it will basically return an invalid address. It'll be like,
In user space, we have Valgrind for that. Can detect that. Is there something similar in kernel space?
I'm not sure about that, no. I have only used KCSAN in kernel space.
This is what I just mentioned. This is the kernel address sanitizer, or KCSAN, which is the same. I mean, it's a bit different than Valgrind because Valgrind instructs at runtime, instruments at runtime, while address sanitizer uses the compiler for that. But in the kernel, you also use the compiler too.
Right. Yes.
Sorry, attached to this memory. You have even KFans. KFans is based on the same principle of KCSAN. So you have probabilistic detection of some memory faults, like use after free or double allocation and so on. And it's the principle is similar to KCSAN, so you have probabilistic detection that is based on the pool that you got from the pool to your memory and so on. So maybe you can have a look of this. KCSAN and KFANS is two standard mechanisms inside the Linux kernel.
That's wonderful. What's the name of the tool that you were saying?
KFANS, I can tell you.
Okay.
I have a question.
Yeah, for sure.
That is linked to this. So I think you are a researcher. So my question is, can you think of extending actual kernel address sanitizer to check if they can detect even data races? Because, for example, KCSAN use a shadow memory in which they track what is the memory that is currently allocated by the kernel, and if you try to adjust this memory, you got a trap.
Right.
And it is done by instrumenting each loaded store at compiler level. So instead of performing single load store, you do a bit of operation before and after, and you go to the shadow memory, you check if your memory is correct, and you come back if this is allocated that you can adjust, otherwise the trap. So maybe you can research if we can extend this mechanism for some kind of data races, because you can in some way track some variable that you detect that are shared by even static analysis.
Right.
And by this, you can in some way make a shadowing of this variable, it is now under read or not, and yeah, try to detect if there are more than one thread that are accessing this by some bit mask and so on. So maybe it could be a reasoning for you for your research.
Thank you so much. What's your name? I'll talk to you after the first
Okay.
session as well. Thank you.
Yeah.
All right. Feel free to connect with me, everyone. This is my LinkedIn. I've also attached the QR over here. And this is the conclusion of our talk, as we are right on time. Thank you, everyone.